Okay, so this is the problem on one of the first problems of force vectors and free body diagrams in the course material. And I think the reason why it might be confusing is because the diagram on the course is not labelled sufficiently. So that 30-degree angle is missing, and so is the right angle. So therefore, although that one's marked at 60, we don't really know what the rest of them are. Anyway, I'll have that fixed, and but while I'm at it, we might as well just run through how this process actually works. So the first thing to do is to draw our free body diagram, and we need to have a vector at 60 degrees. It's not 60 degrees on my sketch. It doesn't matter. And drawing a free body diagram and a force diagram is pretty useful no matter whether we're doing the analysis graphically or by calculation, because it's just a way of getting that system into your head in terms of what is going on. So we've got 15 kilonewtons coming down at 60 degrees. And this force here is also that 60 degrees to horizontal. So we can draw that one in as well. Just flip the set square upside down, line up on the paper here. I'm just using the lines on the paper as a reference. And this is all about process, not accuracy, and we won't mark you down for slight inaccuracies with this sort of thing. We're only really interested in your process. So that's our first unknown vector there. Just darken that a little bit. So, and we've got this other one which is coming back at us at the point of coincidence at 30 degrees. So draw that in with the set square as well. Line that up on the paper. And both of these forces are going to be acting upwards because there's the thing's in equilibrium. So yeah, the only way that this force could be in tension, this one here, is if our applied force was maybe at a horizontal, then this is going to be pulling down because the force would be tending to rotate this member around this direction in anti-clockwise. So we can say that that's also 60 degrees in there. From there, it's a good idea to label the thing. So now we have force vector AB, force vector BC, and force vector CA. And we only know the magnitude of this force. So to draw our force diagram, if we were doing this by calculation, we could just sketch it roughly, and then we could figure out what our angles are from there. So I would say that if we were just going to go by calculation, what we would do is just say, okay, we've got this force coming down at 15 degrees, 15 kilonewtons at 60 degrees to the horizontal, and this is miles out of accuracy. And then there's another force that's going at that angle, so we can just roughly draw that in. It's somewhere there. It doesn't really matter where. And provided our angle is more or less right, so that we just sort of get out, we don't confuse ourselves. And then the other force, this 30-degree force, must connect the two. So if we connected it on the end here, we're never going to get a point of coincidence with this one. So it must start from up here. So that means that given that it's in the upward direction, then we can say, well, okay, this is at 90 degrees in here. Well, then we have a force vector in there, and we have one here, And now we can say that if that's 60 degrees, well then that must be 30 in there, because if that's at 90 degrees. But that's really tiny and not that useful graphically. But if we were then to do the calculations, it still gives us our sense of what how it all fits together. So by calculation, we can then say that if that's 15 kilonewtons, then this must be 15 sine 30, and the AC must be 15 cos 30. So if we say that we've got, we can do that now. So BC equals 15 sine 30 equals 7.5 kilonewtons, and CA equals 15 cos 30. Kilonewtons. So my scruffy little diagram there was enough to get my thoughts in order in terms of what trigonometry I needed to do to calculate that. If we're doing it graphically, and we'll call this force diagram A. So doing it graphically, which is a good way of confirming our calculations, or you can go the other way and confirm your graphical solution with calculations. So in this case, we need to be more accurate, and I'll just use my method that I learned a long, long time ago of transferring these angles, because we drew them in once accurately. There's no point messing around drawing them in a second time accurately. So just draw a line here. And I'm not going to make this very big because I want it to fit on the page, but if you were doing it using the graphical method, you should try and go for the biggest scale that you can get to on the page. But what I'll say is that 15 kilonewtons is equal to 30 millimeters, and so we say force diagram. And that's our free body diagram. Scale equals 2. Oh, we'll just do a little column there. 2 millimeters equals 1 kilonewton. So measure down here and find 30 millimeters. And having done this little roughie, we know which way round this is going to turn out. So that's our 15 kilonewton vector there. And then if we transfer the sense of this one, yeah, we'll find that I think the set square is going to fit in there nicely. Yeah, that's 60 degrees. So the triangle, once again, as we discussed there, has to join up. So if we transfer this one down, to the end of the 15 kilonewton vector, we've now got a semi-accurate force diagram I say semi-accurate because it's so small. So from this, if we label this up, we can go A, B, C, that's 15 kilonewtons. This one here is, now that I know it's 7.5, I'll call that 15 millimeters. So 15 millimeters equals 7.5 kilonewtons, is half. And this one here, 26 millimeters, equals 13 kilonewtons. And that's how we do it. So hopefully that's clarified that.